In this module we talk about setting up Timer D that allows high resolution pulse width modulation on the MSP 430. Here is a set of waveforms that illustrate the operation of Timer D when it's set up in the high resolution mode. First there is a counter called TDR counter, which is here in what is called up mode. The count goes from 0 up to a maximum value that's set by the value in this particular register. That value really determines the number of counts of the high frequency clock that determines the switching period. To that counter value we compare the value in the register that's denoted here as TD0 CCR1. The comparison between these two determines the length of the pulse that is produced at the output. This particular output is TD 0.1. So there are actually two timers inside, TD1 and TD0. The example waveforms here are shown for TD 0. Now the switching period is going to be determined by the number of high frequency clock pulses in the period, and that in turn is determined by, as I said, the value that we set in this register right here. The duty cycle in turn is determined by the value of the present in this register right here, and the duty cycle is simply the ratio of these two numbers. Normally the number n and number k will be much larger than 1, so this picture here does not show the reality. We will have n in the thousands, for example, because the frequency of the clock that is going to be used for the high resolution counter is very high. It's 200 megahertz, which gives us a time resolution of 5 nanoseconds. So to set up the timer in the high resolution mode, there are really 3 steps. One is we have to set up the core voltage to the high value that allows the core clock frequency to be increased to 25 megahertz. Second, we need to set up the high resolution Timer D generator to multiply that master clock frequency by a factor of 8 and obtain the frequency for the high resolution counter to be 200 megahertz. And then finally we need to configure the Timer D modes and set up the switching period, and after that we are ready to issue the duty cycle command and observe the output. Setting up the core voltage and the processor core frequency is related to the fact that the microcontroller starts in a low power mode with the core voltage reduced substantially below 3.3 volt supply by an internal on-chip voltage regulator. So the chip starts in what is called level 0 that operates at a very low clock frequency. So we need to bring the processor to what is called level 3, which corresponds to a high supply voltage and allows the operation of the clock frequency up to 25 megahertz. That is done in steps, so you cannot immediately go from level 0 to level 3. Instead it's done in 3 steps, first to level 1, level 2 and level 3. In the main program that's linked on experiment 2 page, you can see the details of how these functions are actually written. So this completes the first step of setting up the voltage up to the value that allows the high frequency clock for the core. The rest of the lines on this page here are used to increase the clock frequency to 25 megahertz. You will notice at the very end it actually takes some time for the digitally controlled oscillator to settle, and so we need to wait a certain number of clock periods to ensure that the processor is in the state that's correctly operating at 25 megahertz. Alright, now Timer D is a fairly complex peripheral, but importantly it includes the ability to multiply this 25 megahertz clock by a factor of 8 to obtain 200 megahertz clock. It has also the abilities to multiply by a factor of 16, but the maximum frequency cannot be greater than 256 megahertz. So Timer D, there are two Timer Ds on MSP 430. They can be operated completely independently or can be coupled together. Each timer includes a 16-bit counter. It includes 3 capture compare registers that are going to be used to set the switching frequency, this one right here, and 2 that are going to be used to set up independently 2 outputs with 2 independently determined duty cycles. Here is the block diagram of the Timer D, and you can appreciate the variety of blocks inside. This block right here is called high resolution generator. That's the block that's really used to multiply the input clock frequency by a factor of 8 or a factor of 16. We will use times 8 in our code. And then here is the high resolution timer. The high resolution timer is then compared by the content of these registers right here to output the signal depending on the mode that is selected. Okay. So here's the piece of code that configures the Timer D not to operate as a pulse width modulator at 100 kilohertz switching frequency. The top part sets the clock for the high resolution counter to be 200 megahertz. It puts it in what is called regulated mode and enables the high resolution. Now when you look at the code sequence right here, it's impossible to understand what this really means without reference to the appropriate tables in the user's manual. We'll show that in just a second. Okay, so here is as an example, this line right here sets Timer D clock source to be the 25 megahertz system clock derived from the digitally controlled oscillator for the core. And you can see that TDS select underscore 2, you find it in the table right here. That is this value right here, selects the SM clock as the clock input to the timer. There is a whole other variety of choices here, and it is a good idea to look a little bit through the tables that describe registers for Timer D to understand what is going on in the code that is supplied. Here is another example of setting up the control register for high resolution operation. In this line right here, we set the bit TD high resolution enable to enable the high resolution mode. Then the TDH reg enable, it's right here. That actually synchronizes the high resolution clock to the master clock input, and TDHM underscore 0. Look at this entry in the table. 0 right here means that the high resolution clock is 8 times the Timer D clock, and so that's how we get 200 megahertz and 5 nanosecond resolution. Then finally, just as an illustration of another line, this line here sets up how the output is generated. There are a variety of output modes. Out mode underscore 7. Let's find that. This is right here. Out mode 7 is what is called a reset set mode. That actually corresponds to traditional pulse width modulation with a trailing edge that's modulated. And then CLLD underscore 1, find that in the table, it's right here. That is going to load the value to the register at the time when the counter counts to 0, which means at the beginning of a switching period. So that gives you the expected operation of the output. The two outputs here, TD 0.1 and TD 0.2, will be 100 kilohertz waveforms with duty cycles of 0.5 and 0.25, and you can see in the comments exactly how we set up the 100 kilohertz. For example, here is the value of that register that sets the number of pulses in a period. That number of pulses is set to 2000. Since the clock frequency is 200 megahertz, divide by 2000, that gives 100 kilohertz switching frequency. Then the two registers that determine the duty cycle are shown right here. CCR1 and CCR2, they are set to 1000 and 500 respectively, and those correspond to values of 50% and 25% of the duty cycle. So again, this is all included in the main program that's linked on the experiment 2 page, and you can work with that program to get started on high-resolution pulse width modulation. Once you have successfully compiled and uploaded the program on the microcontroller development board, then you can actually locate the output pins, TD0.1 and TD0.2. They are actually pins 16 and 17. We can measure those waveforms with respect to ground on the development board and observe that they behave indeed as expected.